Hi, welcome to the webinar on Versal AI engine, kernel and graph programming. So in this webinar, we'll go through the AI engine implementation on LiDAR data processing. Here is a brief outline of this webinar session. So first, we will discuss the hardware architecture of Versal AI engine, and we'll walk through the ADAS sensor fusion with Versal AI engine architecture. And after understanding the hardware architecture, we'll go through the basic AI engine programming workflow, and after that we'll also try to understand various optimization techniques while programming the AI engine, so then we can decrease the number of AI engine kernels and decrease the computation time. And after this, we can we'll go through some FAQs and have our QA sessions. So let us walk through the brief introduction to the Versal AI engine architecture. So Versal ACAV devices, right, consists of first of all is the programmable logic, and next is the programmable system or processor, ARM processor. So these two hardwares were already available in the previous Zinc MPSoC processor or previous AMD hardwares, right? And but this AI engine or systolic processor is the completely new hardware present in this Versal ACAP devices, and all these programmable logics, programmable systems, and AI engine can communicate through the network on chip bus. And regarding AI engine, like AI engine is a multi-processor architecture. Like each processors are arranged in the form of array, and they are called AI engine tiles. And each AI engine tiles consists of this processor BLIW, very large instruction word processor, along with its own dedicated local memory. And all these AI engine tiles are able to communicate with each other through stream or buffer interface, and they can also communicate with the programmable logic and processor programmable system through memory and stream interface. So when you go for single AI kernel, right, so it is a vector processor, so you can do parallel computation, parallel data computation like multiplication or any processing computation of in the bonds of 16 or multiples, like parallel computation you can do with in a single cycle. And it also has various DSP signal processing related hardware architecture or data path. And due to this vector and DSP supported hardware architecture, we can do various parallel processing in video and image processing like application, and mostly in signal processing applications. And for machine learning inference architecture, like we can do all the machine learning related computations by designing your locally or your own custom hardware architecture using the AI tiles. And AMD also provides the one IP, NPU IP, which we can run over this AI engine tiles. Regarding programming of this AI engine, there are two steps. First is the AI engine kernel programming, where you program the individual each kernels, like each kernels separately, so you can divide your processing pipeline into multiple components and program the individual AI kernels. So it has C++ based APIs for programming these individual kernels, and after programming the individual kernel, you connect these kernels. So that step is called AI engine graph programming. So in this graph programming, you combine these multiple kernels, connect these multiple kernels to create the whole complete processing pipeline. And during this connection between these kernels, you also arrange the memory or transform the memory from one format to another using some tiling parameters. And in the right, like if you see this graphical representation, first and second are the AI engine kernels. Like you program this individual AI engine kernels using AI engine kernel APIs, and after programming these kernels, you connect this first and second kernel using graph programming API, and you also connect the interface, input interface and output interface using graph programming. Okay, so next we'll go through the ADAS sensor fusion example, like how we are using this various AI engine processing for our LiDAR processing and also for other AI related inference processing in the AI engine kernels. But for understanding the AI engine basic feature, will be more really focused in LiDAR data processing. So here is the hardware architecture for the ADAS sensor fusion solution, which we develop in Logictronics. So for processing part, like we are using Versal VEK 280 platform, and it consists of GMSL. Like we are using for sensor, right, sensor input part, we are using GMSL cameras and ultrasonic sensor for park assistance and driver assistance related application. And we are also using LiDAR data for creating the 360-degree point cloud data view and doing processing in that LiDAR data. And we also have Canvas running in this platform for communicating with the ECU system of the vehicle. And for visualizing the output and logging, right, so we are using HDMI based display for displaying all the sensor or LiDAR or ML related outputs. And we also have 10 gig Ethernet interface for logging and debugging the sensor data. Regarding the software architecture, right, like we are using single chip sensor fusion architecture. So in a single chip we are interfacing all the sensors, and we're also doing computation using AI engine trials and running the ML pipeline in a single chip. So for in the AI engine tiles, we are doing basically two tasks. One is LiDAR data processing, and another is running the ML pipelines. For LiDAR processing part, we are using two custom AI engine kernels, one for range image to point cloud data conversion, and next is segmentation or detection of ground in the LiDAR data, and also object object detection in the LiDAR data. And next, in the AI engine, we are also running two vision machine learning pipelines for detecting objects in the data from the camera. And next is we are also running another single ML pipelines for detecting object in the LiDAR point cloud data, and this is running in the NPU in the AI using NPU IP. And next, for visualizing this LiDAR data and ML pipeline data, we are passing the output to the HDMI monitor using HDMI IP, transceiver IP running in this platform. And it also has 10 gig interface for logging the sensor data and for debugging purposes. Okay, so regarding LiDAR data processing, like when you do LiDAR data processing, there are basically three things types of processing we can do currently. Right, first one is conversion range image data to the point cloud data conversion, and here we just convert the range image or polar coordinate data into the point cloud three-dimensional Cartesian coordinate data using trigonometric computation. And next is for LiDAR data is segmentation or filtering the range LiDAR data, right? So here we do ground segmentation, where we can remove the ground data from the LiDAR data. So for this we use the connectivity between the LiDAR range data in horizontal direction, and using this distance between the horizontal range image data, we are able to detect the ground. And third type of computation is detecting objects in the LiDAR range image or object segmentation. So here also we are using connectivity based horizontal and vertical direction connectivity based computation, and using this connectivity data we are able to label the object in the LiDAR data. So using AI engine, right, we are able to do various parallel computation in the LiDAR data. So for range image to point cloud conversion, so we can utilize AI engines, vector processing, and multiple processor computation architecture, right, to do the parallel computation of the a range image to point cloud conversion. So first one is like how is this is possible is each AI engine can compute vectored do computation using vectored operation. So this is basically doing parallelly handling multiple data by a single processor. So it is called parallel in data type of processing. And next is like since we have multiple AI engine tiles, so each tile can handle so we can like partition our range image among these multiple tiles. So our single frame of our range image is divided into multiple AI engines for doing parallel processing. And for ground and object detection also, like we can do same vectorized operation for both horizontal and vertical connectivity calculation. And further we are also doing labeling using connected component labeling using vectorized operation and partitioning the connectivity calculation into the multiple tiles. And after processing like multiple parallel computation, data are passed through stream input and output to the PS or PL depending upon the hardware architecture. So regarding the range image to PCL point cloud conversion algorithm, for parallel computation, like we have in the AI engine, here are the various steps. Like first one is the decode step, where we take input from the Velodyne SDL64 LiDAR. So through the so this data is passed to the our VK280 platform through the Ethernet interface, and this data is decoded and converted into range image consisting of 64 rows and 1800 columns, or you can say it consists of distance for each channel, and in its 360-degree rotation it is divided into 1800 columns, corresponds to 1800 columns. And first level of parallelization in AI engine is done through dividing the partitioning the data into multiple chunks, and this is called parallel computation in AI engine. So here we are dividing our range image frame into 7 part, right? Single frame is divided into 7 part, and further this range image is partition is passed to the each like AI engine kernels. So we are using 7 AI engine kernels to process 7 range image partitions. So apart from this, next level of parallelization is done in data level. So here each AI engine kernel, right, after receiving it partition input, each AI engine kernel also computes 16 vectored input, 16 channel you can say, at the same time, and generate outputs, do the vector computation and generate output for the 16 channels in the single run. So here is the more graphical representation of the software architecture. So first of all, our host application will receive the LiDAR data and convert that into the range image, and this range image is passed to the memory to stream HLS PL kernels, which converts this one single frame into multiple 7 partition input, so that this 7 stream is passed to the 7 range to point cloud kernels. And after doing the vectorized computation in each range to point cloud kernels, it generates the output, and it is passed through the stream to the again through the stream to memory PL kernels for converting the stream into the memory chunks. And this memory chunk is again is passed to the host application host application, like which is running in the PS. So it will this memory is mapped to the host application through the PS. Okay, so this is more detail on the processing pipeline in the each individual AI engine kernels. So this so each range image is first partitioned into 7 parts consisting of 256 columns. So each AI engine kernels is computing the 256 columns of data range image data. So, and these all 7 engine kernels are identical and handles this 256 cross 64 range image data. And here, like when you see the like first step is like loading the 64 column data of the range image into the AI engine kernel, and for processing the vector data in terms of 16 in 16 vector data in 16 vector count, right? It is splitted. 64 channel data is again further divided into 16 channels, and this 16 channel data is passed to the our next step, where we do the vectorized computation for range image to the point cloud conversion. And after that we'll also receive the vectored output, and we do the memory arrangement for this vectored output using tiling parameters, and pass the output through the stream interface. And for host application which is running on PS, we use HLS stream to memory kernel to memory map those stream to the PS host memories devices. So after programming the AI is individual AI kernels and graph programming, we'll put that into the our platform, right? Platform design, and after that we can get this whole design you can view in the Vivado. And you can see here in the right side all the AI engine related PyDisk related kernels are present in this one single block, and all other hardware designs like HDMI, Ethernet are also present in this design, final design. And if you go for look into the PyDisk region only block, right, when you go for detailed view, it will consist of various HLS PL kernels and all the interface blocks, and one block for your all the AI engine computation. Okay, let us go into the AI engine programming workflow. So before going to the engine kernel programming, we look into the numerical computation, like what will take to convert range image data to the XYZ point cloud data. So each AI engine kernel is doing 16 floating point computation, and for whole graph, like input for is taking input LiDAR range image data consisting of 64 rows and 1800 columns. Now this range image data, each row corresponds to the LiDAR channel. So in case of our Velodyne HDL 64E LiDAR, 64 channels, each row corresponds to these 64 channels, these 64 rows, and this channels has this is located at certain angle called elevation angle, and each column of this range image data corresponds to the LiDAR's rotational position alpha, right? So this azimuth angle, it is called azimuth angle. So each this column in range image data, which consisting 1800 columns, corresponds to the angular position of the LiDAR, single LiDAR in 360 degree rotation. So we use this elevation angle and azimuth alpha angle, its sine cos values at that point to along with the range image data to convert this range image data to the XYZ point cloud data. And in our AI kernels, each individual AI kernels in one run, it is taking 64 LiDAR data frame and further converting it to the XYZ point cloud data. So let us go for the first kernel programming step in the range to PCL kernels. So each range to PCL is range to PCL kernel AI kernels are doing vectorized 16432 data computation. So first step in this computation is load step, like loading the input and constants. So for loading and loading the values, or taking the input from the stream interface which comes to this individual AI kernels. This kernel APIs like read increment, read data from read increment underscore v, and load underscore v is there. So each this APIs has this suffix underscore v, which works for the 16 certain size of float or certain data type, depending upon this template values. So after loading constants, for like first we are in the first, if you see this example here, data in 0, here we are loading the 16 floated to range image values from the input stream, and in the second example you can see we are loading some cos and sine angle constant values into this vectored datas. Next, if you look into the next step is after loading the data, you do the computation, and in our case we are doing vector multiplication and vector to scalar multiplication. So this APIs can support APIs, and also our AI engine hardware or processor, BLIDOL processor can support for vector to vector multiplication or vector to scalar multiplication or computation, you can say. So in this way our range image data is converted to the PointCloud data in our AI engine kernels. And in this example, like we are doing 16 channel computation for each steps here, and this is repeated 4 times so that we can have 64 channel computation in our single run or single iteration of this computation. And we'll do the multiple, like for 256 column we'll do for 256 iteration of this computation. And while doing this computation, one thing you have to notice that instead of getting single like xyz x1 y1 z1 point cloud or x2 y2 z2 point cloud in serial manner, right, what we expected, but due to this vector multiplication or vector computation, you will get packed data, you can say, in such a way that you will get 16x coordinate, 16y coordinate, 16z coordinate in that way in the memory. So it is the with the help of kernel other programming next styling parameter and other programming APIs, we have to convert this packed data into our required format, x1 y1 z, this unpacked serial format. So after this we know how each kernel is computation is going on. Next we'll look into the graph programming of. And for graph programming there are 2 options depending upon the data movement, like your how the output are processed in your graph. So first one is using only AI kernel tile only, you process the memory also. And if you see here in the right side, This is one of the graph architecture one, where we use only AI kernel tiles for processing the outputs. And in the next architecture, second architecture, we are using another type of tile called memory tiles. uh, Memory tiles. So in the graph architecture one, like if you see here, it consists of 7 range to PCL kernels, and and it is passed through the buffer, and further it is passed to the pass-through buffer, pass-through kernel. So it is a dummy kernel which do two things. First is arrange this 16 packed data to the unpacked data, and convert buffer memory to the stream output. So in total there are 14 AI kernel tiles are used for computation, and further this buffer, depending upon the buffer, more tiles will be utilized. So after compiling this graph and all this point range to PCL kernel programming compile, you will get the compiled say build, right? So after build, you can view the arrangement of the graphs, like arrangement of components in the graph, how those individual AI kernels are are connected in your graph using this graphical graph view present in the PyTest tool. And here you can see in this graph, this range to PCL kernels are located in the input side, and we have some double buffering going on in this in the middle during the connection between two kernels, and pass-through kernel are present in the output side, which converts the output to the stream format. Next, also after after a build, you will get the array view of the graph. So this view will give you the actual location, like where your tiles are running, where your processor and your buffer memory are located. So this will give you the rough tile utilization, like how much tiles are occupied, and location of your graph in the AI engine tiles. Now this is the second graph architecture. So here we are using memory tile in the output side. So here in the input side we are using same 7 range to PCL kernel, but for output side we are using 4 memory tiles, and 3 of the memory tiles we are connecting to range to PCL kernel outputs, 2 channels of range to PCL kernel outputs. So we cannot do more than 2 kernels due to the limitation of our memory tiles. So memory tiles are just tiles which consist only memory blocks, and it is 512 kilobyte. So and it can be accessed by multiple engine compute tiles. So in this way we can decrease the number of processing tiles and pass the output to the memory tiles instead of another processing compute tiles. So this will help to decrease the number of AI engine tiles in one way. And next, you also come to know how these memory tiles are utilized in the AI ML architecture. So here this is the second graph architecture, and after building this graph you will get similar graph view here. Here you can see 7 range to PCL kernel. Then after that we have 7 double buffers, and this is connected to the memory tiles, right? And from memory tiles stream output is coming out. And this is the array view. Here you can see various location of the compute tiles, memory tiles. Here in the bottom 2 row are for memory tiles, and upper ones are for compute tiles. Here you can see this is the automatic allocation of buffers, memory tiles and AI tiles. So you can see that by default AI that by this tool is able to allocate the tiles your of the graph at the random location in the AI engine array, right? So if you view the resource utilization of this graph along with the graphs visualization part, you will also get the report for like various how many tiles is occupied by your graph, like your 7 compute tiles are occupied, and apart from that 10 tiles are occupied for buffers, and for memory tiles 4 memory tiles are utilized, and for interface other counts are there. So due to automatic placement, buffers are allocated not at the same location where compute tiles are assigned. So due to this, more tiles will be utilized. So viewing the previous AI engine programming flow, you can see that default programming APIs and all those default, like if you don't give any optimization if you don't use any optimization API, your graph will be occupy more AI engine tiles, right? And it will also say take more, computation time will also be large. So we'll look into some optimization workflow, like how we can decrease the number of tiles and decrease the latency also. So first, graph optimization, like you can say, for decreasing the number of tiles is using location API. So here we give the location, we give the location for placement of the buffers and stack, so that we can control the placement of the buffers. So there are two types of location you can assign for your buffers. One is absolute location, so you can give the row and column of the tile number where you want to store the buffer and stack for the particular tile. And another is the relative location, where you can assign give the name of the AI engine kernel corresponding to which AI engine buffers has to be allocated. So in our range to PCL kernel graph, we are using relative location, and while giving this location, we have to consider two things, like our memory should fit into this 64 kilobyte tile memory. This is local memory bank, and if you go for double buffering, you can only save data of 32 kilobyte size. So your buffer or any stack or heap memory should fit into this memory size. So here is how the API looks like. So here we assign, we use the location template, and then we provide the name of the buffer for interface for the buffer, and then we give the location. Here again you use the template, kernel template, then kernel variable template, and we assign the name of the kernel, like range to which kernel our buffer has to be allocated. So after giving this location API, after using this location API, if you view the array assignment, right, array view of the compiled graph, you will see that the buffer and stacks are located in the same location where AI kernel compute is going on. AI computation processor is running. So in this way, our previous 10 buffer utilization has dropped down to 7, decreasing the tile utilization. Next is, if you see the previous array allocation, it is assigned at a random location in the whole AI array. So while running multiple graph, right? Currently we are running only range to PCL graph, but if you are running for multiple AI kernel graphs, then this automatic assignment will make your array make your graph, or say AI kernel utilization very difficult, right? It will be assigned in very different position. So to localize this inside this AI engine array, then there is a second optimization step where we can assign the particular column region in the AI engine tile. So for example, here we are using starting from 18 column, and it is spanning to 7 column, starting from 18 span 7 column array for this range to image partition. So after fixing this location, our tiles or our graph will be allocated in this region only. So here is the array view of the range to PCL kernel after assigning the partition. So in this way we can run multiple graphs, after partitioning the AI engine array into multiple partitions, we'll be able to run multiple graphs in the AI engine array. And next type of optimization, especially for AI ML architecture, we can use memory tiles instead of using AI engine tiles, computation tiles. We can use memory tiles. So this memory tiles is like just memory. It doesn't have any processor. So it is size of 512 kilobyte, and when you do double buffering, you can only use 256 kilobyte of data size. So if you go for single buffering, you can use a whole 512 kilobyte memory, but there will be some latency due to the read-write cycle of this single buffering memory. And when you go for double buffering, as the memory size is decreased, but due to the parallel read and write option for this double buffered ping pong buffer, you can say it is said as a ping pong buffer. So this will help to do parallel read and write into this memory tiles. And here is one of the example how it affects the latency due to the memory tiles single buffering and double buffering. This is the trace of the range to PCL kernel when we are using single buffered memory tile. As you can see, for 32 iteration, we are running for 32 iteration, and for 16 iteration, one frame will be completed, and it's after certain run, okay, our memory tile will be filled, and it will retry cycle will processing of the memory tile will be going on, and during that time our processor will stall. So due to that, our processor latency, like processing latency, will increase. And when you go for double buffering, your processor will be running continuously without any stall right here, and your memory tile data transfer is also going on in parallel while doing the processing by the memory tile during the computation, our compute tiles. Next type of optimization to decrease time is decreasing the input output latency read-write during the read-write cycle of the input output. So one of the optimization is you can change the width of our stream interface and read multiple data at the single our stream interface processing. So for example, in the 32-bit stream, your data chunk data will be read as a 32, like a single 32-bit data. So our flow 32-bit data will be present in the single data of our stream input. And when we go for 64-bit interface, this 32-bit data to 32-bit data we can do simultaneously, like in a single stream read operation we are able to read two data at the same time. So due to this our input will be loaded more faster compared to the this due to the small size of stream. We are able compared to the small size stream, double the 64-bit stream will be more faster compared to the this small size stream. So we can increase this to multiple, like 128-bit, and read multiple input at the same time. So this will decrease the reading of input and decrease the latency during the input cycle. Next, after when you go for vector processing, right, we'll look into the tiling parameter, like how this will change the our processor like capability, or this tiling parameter. What does it does is it transforms the input or output data into the some from vector data or packed data to unpacked data, like that. Depending upon your requirement, you can transform the memory data. So if you go for processing like or processor based approach, you will do some looping, and you read a certain chunk of data in single loop and do the some chunk by chunk memory read you do, right? But in case of AI engine, you can use tiling parameter, where it is hardware based memory DMA handles to transform certain kind of data memory into the our required memory format. So you can convert the intermediate data into various formats and pass to the further to the AI engine pipeline, or to the say to the output side. So in our case, our 16 packed data, 16x, 16y, 16z data has to be converted into the x1, y1, z1, like that individual point cloud data. So for that, this tiler parameter has this variables. First one is the buffer dimension. So this is the whole size of the buffer, like where the data is stored. So in our case, 64 cross 768 is the buffer dimension, and then is the tiling dimension. This is like small size of the tile of the data buffer, which has to be used for the transformation. So it is like a small component of this whole buffer memory, which is to read and write in each step. And offset is like where to start from read and write of the data. So mostly 00 means starting from origin you read the data. Then traversal is like how much this tile has to move. So this is like a looping variable in the for loop, right, to read the to move the memory into your memory array. So it has a dimension, like in which direction you want to move, and how much stride is like how much steps you have to move from in each direction, and wrap means how many times you want to repeat this step. So if you see the following example, where we are converting our 16 packed data into the XYZ individual unpacked data, your 64, 70, 68 is the buffer dimension. Then 1 cross 3 is the one like single dimension, like we are using x1, y1, z1 from this 64, 70, 68 buffer, and we are starting from 00 origin point, right, and we are traversing in two direction. One is in the row dimension, we are moving single step and we are repeating this 64 times, and in the column direction we are moving three steps ahead and repeating this for 256 times. So here is the pictorial view of the above implementation of tiling parameter to transform this packed XY point cloud data to the unpacked unpacked point cloud data. So if you see here, this is the main output from the AI engine kernel. Okay, so here this tiling dimension 1 cross 3 is this one, from starting from x1 y1 to z1 1 and this tiling this is the dimension which will move this memory. This much memory will be moved in the row direction and in the column direction. So in the row direction we are using single step and incrementing till 64. Then again in the column direction we are moving 3 steps from here to here, right? From here to here it will go there, and it again repeat to the down direction. In this way we traverse this whole memory, and convert will receive like this whole unpacked data in form of x1 y1 and z1 in the exact like point cloud data, which we can pass to the ML pipeline or for visualization. Okay, next we are going we'll look into what is the difference between AI engine and AI ML architecture, and how to migrate from one to another. For kernel programming part, like one of the most important is like number of interface, stream interface. In AI engine only it only supports 2 stream inputs outputs, but in case of AI ML it only has single stream input output. So you have to combine this stream or 2 stream into a single stream, or flatten this stream to single stream to process into the AI ML. And next, for graph programming part, you can use AI engine tiles does not has this memory tiles present. So all the processing, all the memory operation has to be done inside the AI engine compute tiles only. But in AI engine AI ML architecture, you have memory tiles. So apart from computation tile, you have this memory tiles for one for arranging the memory from, like we have seen in our application, and to convert that, pass to the next step. Okay, so next we'll look into this how we process the output and visualize into our HDMI monitor, which is connected to the another processing hardware. And for host application, all the point cloud data is returned into some single frame point cloud data is obtained from the range to PCL kernel. And similarly, color coded labels, you can say labels will be generated from the range to segment or say another kernel, which will give the labels, and that labels is used as a color to code the various like ground and objects. So here you can see in the right hand side, you can see the output rendered, where this light blue color is labeled as ground. Okay, and other like individual clusters are labeled differently, and depending upon this values, this colors has been rendered. And to render this output, OpenGL based application, ES based application is developed, which runs on the Mali 400 GPU. Okay, so we'll watch the demo, like how the output looks like. So here in the left hand side you can see the range image output, which runs in the AI engine kernel, and the right hand side ML outputs. So in the right hand side you can see the object detected here in the camera frame and in the LiDAR frame.